Okay, so now look at the example 3, where this one I'm taking from, again, past year final exam, but long time ago, 2005, 2006. Okay, but this one a bit more general question, where they give you something, something different, because now they give you, they sketch the region for you. Okay, so we have the region that we have is part of the circle, where we call that as a sector. Okay, and we have a lamina, the word of lamina, meaning that if you want to get the mass, so we have to apply your formula of double integral, because you have to take note that for mass, it can be solid, which is triple integral, or double integral. Okay, but now because we just discussed on double integral, so we'll just look at the lamina. Okay, but it is possible to be asked about the mass of solid. Okay, so now we have the sector, where it based on the circle radius A. Okay, radius A, and the angle is beta. Okay, angle, you do know how to read the angle for polar. You have to start from the x-axis positive. Okay, so that is your region looks like. Okay, so now in this case, they said that if the lamina has a constant density, so constant density, so the lamina here, the density is constant. Use double integral in polar. You have to solve in polar. You have to answer this. So show the area of lamina. They don't mention show or find the mass. Okay, but now you look at here. You have learned about the area. You are given a region, and they ask you to evaluate or obtain the area of that region. So you can use the double integral, where your function integrand here is constant dA over the region, right? Okay, now we relate that with the mass. So what is the formula of mass? We also need to use double integral, and you need the density function and dA over the region. So in this case, they said that we have the density function is constant. Okay, so I think the instruction here should be more clearer. So they have to provide the density. We understood this is a constant, but it can be 2, it can be 3, it can be k. But in this case, to obtain this one, we should have the density is equal to 1. So in this case, the density is, when the density is constant, which is equal to 1. So now it turned out to be 1 dA as well. So in this case, the area and the mass have the same value. Okay, because of only this particular case, where the density is equal to 1. But if your density is 2 or 3, and then you cannot say that the area is similar to the mass, but only for the density is equal to 1. Okay, why we can have the density here, the density constant or equal to 1? Because it is stated that the density is constant. Okay, remember from the previous video, I already explained to you about the terminologies, the center of mass, or sometimes we call that a center of gravity. Sometimes we can say that we don't say that as a center of mass or the center of gravity, but we say that as a centroid. So how can we have a centroid? It is actually the mass, the center of mass, but when the density is equal to constant. Okay, so meaning that the center of mass, the center of gravity, which is there is a x bar and there is a y bar, it is called, or it is namely as a centroid when the density is equal to 1. Because I give you an example, an exercise, but some of you be confused. why we set up the density is equal to constant, because it is mentioned that the density, the centroid, they don't say that the center of mass. It is in the instruction, it is saying that about the centroid, so it is understood that the density, the density function or the integrand is constant. Okay, so now in this case, the mass and the area of the lamina or area of the region are the same, because we have the density is equal to 1. Okay, so now because the question is asking about the area, so using this formula, so now you have to solve that in polar. So r d theta. So the theta obviously for this region, so the theta is 0 to beta, and your r is 0 to a. Then when you solve that, so since it is given, so I don't want to solve this. You can just look at the slide here. So based on this, dr, d theta, so I provide the wrong. So theta beta and r is a. Okay, and when you integrate, and you will get this one as stated. So it is shown. And then from there, you have to find the centroid. So remember, if you want to obtain the centroid, why it is named as a centroid? Why they don't say that the center of mass? Because our density function is constant, which is equal to 1. So in this case, remember the formula of centroid, you need to obtain the mass. But in this case, the mass is the same as the area, which is this one. We already obtained that. So this is also the mass. Okay, so that is also considered as the mass. Okay, because we have the density is constant, which is equal to 1. Okay, so now in order for us to obtain the centroid, we have to obtain the x bar, y bar. So you need to compute the my, the moment of mass, and also respect to y and respect to x, because we already obtained the mass from the area over here, up here. So this is already done. So now first find the moment of mass. So with respect to y, so you have to put the x here, density is equal to 1, and then you have x, so you have to, because you want to solve using polar, so you have to replace the x in terms of polar, which is r cos theta, and dA is r d r d theta, and we should use the same limit, because our region here is the same. Okay, so the question I in Roman and II will refer to the same information here. So that's why you can use the result in I here. By using the result here, you have to calculate the second part. Okay, so now I'm sure that this is not so complicated. You just integrate r, so you got r squared over 2. Okay, so I'm sure this is typo, I think, but the final answer should be the same. You can try yourself. Okay, and then when you substitute r is constant, so your answer is just in terms of trigonometry, just a cos. So you want to integrate the cos, you will get the sine, and substitute the theta from 0 to beta. So you will get, so the moment of mass with respect to y is this one. So now we want to compute the moment of mass with respect to x. So don't forget to substitute the y, and the density is equal to 1, and using the same limit, because we have the same region, and then we just integrate. Again, it's not so complicated. Okay, so you will obtain that this is your moment of mass with respect to x. Okay, and then when you put into the formula of the centroid or the center of mass, okay, so actually this is also called as a center of mass or the center of gravity. Okay, and we put all the result that we have from the beginning here, and divided by the mass, which is the area, and you finally will get this. Okay, so this one looks, you have to understand this one is a question from the final exam. So now let's look, yeah, I mean, you need to spend some time, so that's why the mark here is 8. Okay, 8 for me, quite a large mark for you. Okay, and if you got all correct, you will get a 4% in your hand. Okay, so that is the example about the mass and moment of mass for Lamina. Okay, so now we want to look at the moment of inertia. Moment of inertia denoted by I. Okay. And sometimes it's mainly as a second moment of Lamina. So something missing here. So moment of inertia, or another name of the moment of inertia, we call that as the second moment of the Lamina. Now we are talking about the Lamina. Okay, so we still use the density function. We can see the density function again. And okay, now we'll look at the formula here. Because we are talking about the Lamina, which is double integral. Okay, Lamina, moment of inertia, or second moment of a Lamina. So the keyword here is Lamina. Once you can see the word Lamina, so we always bear in mind that the formula that we have to obtain, for us to use is double integral. Okay, so the second moment of the Lamina about the x-axis, about the y-axis, and about the z-axis. Okay, now look at the formula here. About the x, because they're asking about the x, then you have to put the y squared, and the density is through there. And then if they ask about the second moment, or moment of inertia about the y-axis, so you have to put the x squared. But if they ask you to evaluate the second moment about the z-axis, so because we know that the z depends on the x and y, so it looks like it is the summation. So actually, what we can say that the second moment of the Lamina is the summation of Ix, the second moment, okay? Ix and the second moment of Lamina about the y. Or we can say that because Ix plus Iy is just a x squared plus y squared, and then we can have the, just substitute directly, we have x squared plus y squared and multiplied by the density function. Okay, so remember Iz, so the second moment, so this is I, the second moment about the z-axis is the combination of the second moment of x and second moment of y, or using the formula, it is just the x squared plus y squared multiplied by the density function. Okay. Okay, so now look at the example 1 about the second moment, or moment of inertia. Okay, so we have the density. In example 1, we are given the density function is a function is x squared 5. And the Lamina is a region in the plane that is bounded by the parabolic and the lines of x equal to and y equal to x equal to 2 and y equal to 1. Okay, sketch the graph. So we have a quadratic y equal to x squared, and also the line of x equal to 2. So when x is equal to 2, so we obtain that when we substitute here, when x equal to 2, so y is 4. Okay, and then we also have the y equal to 1. So when y equal to 1, so the x is equal to 1 here. Okay, how can we get that? So when we have x equal to 1, so x is plus minus 1, and because this one is located on the first quadrant, so x is positive. Okay, so now based on the information provided here, where is your possible region should be? Lying bounded by the parabolic and the line of x equal to 2 and the line of y equal to 1. It should be inside here. Okay, so that is your R. So now we we have to look at what is the question asking for. Find the second moment or moment of inertia of this lamina about the x and y. So you have to find out the ix and iy. So what is the formula? So let's say we want to solve for ix. So double integral. So the density function is x squared y. And you have to, because they ask for the admin, you have to have y squared dA. Now, when you actually simplify this expression, you will get y cubed x squared. And then how about the order of integration? So you want to have x constant or you want to have y constant? Okay, for me, I will use the x constant. So when x constant, so I have that particular line. So then we can see that x constant, so x is lying between 1 and 2, right? And then y is, so this is lower bound and this is upper bound. Lower bound is for y equal to 1 and the upper bound is part of the quadratic. So y equal to x squared. So I have dy dx, x constant, 1 to 2. Okay. Sorry, you cannot see clearly. So y constant, x constant and y function 1 to x squared. Okay, so that is our second moment or moment of inertia about the x-axis. Okay, so firstly you have to integrate with respect to y. So x constant, so you have y 4 over 4. Then replace the limit of y from 1 to x squared dx. Okay, so when you substitute, you have the x squared. So I just put 1 over 4 outside. And I have x squared here, so we just replace the y. And we get x squared to the power of 4 minus 1. And then expand. And then after that, integrate with respect to x, and then you get this. Okay, so then by referring to the answer provided in the notes, and please evaluate yourself the answer here. Okay, just use the calculator to evaluate. Okay, now for ix, similar idea, we have to put the density is x squared y. This is the density, and then because we want to get I, the second moment about y, then you have to put the x squared, and then you got x4, okay, x4y divided by dx, and you have to use the same limit because the region is the same. We have the similar region here, okay, and then this is because we have a polynomial here. So now we just proceed with the integration, and you get this one. And please evaluate yourself. Okay, so please do it yourself to complete the answer. Okay, so that is for the mass and moment of mass, and the second moment, or we call that as a moment of inertia for lamina. So now we proceed to, we have done for the first part of the chapter 3. So now we look at the second part of the chapter 3, which is triple integral. Okay.